All right, our second video of inverse trig and natural log derivatives. We're going to practice a few of our inverse trig derivatives just to make sure that everybody remembers. If you were to see arc sine of something, of x in this case, it is the same thing as the inverse sine of x. They mean exactly the same thing. Arc has something to do with actually the arc of the circle and where the angle would be that's associated with it, which is why we call it arc, or as opposed to maybe inverse, but they actually mean the same thing. Okay, so h of x. H of x here is the square root of 1 minus x squared times the arc sine of x. So when we do the derivative here, it's going to be a product rule. So our derivative is the derivative of the first term. Remember that the 1 minus x squared is this, to the square root of that is the same as 1 minus x squared to the 1/2. So we would have to bring the 1/2 out to the front and reduce the power by 1. It's a chain actually, so don't forget the chain part, which is multiplying it by the derivative of the inside, which is negative 2x. So that's the derivative of the first times the second, arc sine of x, plus the derivative of arc sine, the derivative of inverse sine, is 1 over square root of 1 minus x squared. And it is just x, so I don't have to worry about any chain rule there, times the first, which is the square root of 1 minus x squared. That's really nice and convenient, because these are going to cancel out, leaving us just 1. Let's go ahead and clean up the h prime of x part over here, which is going to be, let's see, the 2's here are going to cancel out. A half times 2 is gone. It's 1. I've got a negative x, which is going to go on the top. Arc sine of x goes on the top. And then this whole thing with the negative exponent, 1 minus x squared, goes on the bottom to make it a positive exponent, and then plus 1. Okay, really not much of a reason to do anything else other than that. You could create a common denominator out of 1 and combine the numerators, but not really doing us any good there. Okay? In f of x, again, I've got a product rule. I've got x times the natural log of the arctangent of x. It's crazy looking. Okay, here's my first term. Here's my second term. It looks like the second term, the natural log is not just x. It's the natural log of the arctangent of x. So we'll have to incorporate the chain rule there. Derivative. Derivative of the first is 1 times the natural log of arctangent of x. So that's the second. Plus the derivative of the second, 1 over the argument, 1 over arctangent of x, times the derivative of the inside, which is the derivative of derivative of arctangent of x, which is 1 over x squared plus 1, times the first, x. Okay, and not much you can really do here. We don't need the 1 out in front of the natural log from the first part. We can put the x on top and multiply the two denominators together. I'm not going to write all that out in this case, but that's what you could do. All right, we are actually not going to do this one because it's got an inverse secant. Haven't really talked about that one. And we are not going to do this one because it has an inverse cosine. Just to let you know, if you're super curious, the derivative of inverse cosine is the same thing as the derivative of inverse sine, except that it's negative on the outside. That's it. But that is all we are going to do as far as that one is concerned. Okay, now let's get to something slightly more interesting. Something which is called logarithmic differentiation, meaning that we can figure out how to take derivatives by using properties of logs to do it. So here's the idea. We're going to take logs of both sides of an equation and then use the properties of logs to simplify the equation, and then we're going to go ahead and differentiate implicitly with respect to x. That way we can actually solve for y prime or dy over dx. So if you were to look at this one, first of all, looking at that, that would be pretty complicated to do as a regular derivative. I mean, it could certainly be done. Your whole thing would be a quotient rule. When you do the derivative of the top, it's a product. Within that product, because of the square root of x squared plus 1, you have a chain. And then the denominator also has a chain rule in it. So it'd be a lot to keep it all straight. It can be done, but probably not something we want to mess with. So I'm going to show you how actually using log properties is going to make this easier. So the first thing we're going to do is we're going to take the natural log of both sides of the equation that's given to us, which means that we're going to get a natural log of y equals the natural log of the entire right side, x to the 3/4 square root of x squared plus 1 all over 3x plus 2 to the 5th. We are taking the natural log of that whole thing. Why do you think, you might be asking yourself, does this make anything easier? Well, let's see. I'll leave the left side alone for now. If I use properties of logs, it says that I can separate anything which is being multiplied or divided in my argument through addition and subtraction. So I'm going to get the natural log of x to the 3/4 plus the natural log of the square root of x squared plus 1 minus, because it's being divided, the natural log of 3x plus 2 to the 5th power. Okay, that already should look a little bit easier because of the fact that I've gotten rid of the fractions, but we're going to make it even easier yet. Again, leave the left side alone for now. Remember that you have powers now, or exponents of your arguments. Those can be brought out to the front of your logs. So this will become 3/4 natural log of x. Remember that the exponent on the x squared plus 1 is a 1/2 power, so I can bring a 1/2 out. Remember, you're not taking a derivative yet, so we're not reducing powers or anything like that. We're just using properties of logs to bring the exponents to the front. And then minus 5 log 3x plus 2. Now we're finally ready to actually go ahead and take a derivative. So when I take the derivative of the right side of this equation, 3/4 is a coefficient. The derivative of natural log of x is 1 over x. So it's 3/4 times 1 over x. That one's done. Okay, 1/2 here is a coefficient. The derivative of natural log of x squared plus 1 is 1 over the argument. So 1 over x squared plus 1 times the derivative of the argument, which is 2x. That one's done. 5 is a coefficient. The derivative of natural log 3x plus 2 is 1 over the argument, 1 over 3x plus 2, times the derivative, which is 3. That part is done. So that derivative was actually not that difficult to do when we simplified it using log properties. We'll go ahead and clean this up here in just a second too. But don't forget, we took the derivative of the right side. We also have to take the derivative of the left side, which means I have to take the derivative of natural log of y. Same basic idea. It's still 1 over the argument, which is y, but times the derivative of y, because this is where the implicit comes in, dy over dx. Ultimately, that's what we're trying to find, is dy over dx. So the easiest thing to do here is to multiply both sides by y. So we're going to get the dy over dx. Now I'm going to go ahead and clean this up. This is going to be 3 over 4x, multiplying the first one together. And the second one, the 2's are going to go away, leaving us with an x over x squared plus 1. And then the last one, it looks like the 5 and the 3 will get multiplied on top, over 3x plus 2. And then we have to multiply both sides by y, and that's what you would get. The only problem is, this is a derivative with respect to x, and we don't want to have y's left over if possible, and we don't need to in this case, because y was this function right here. So I can plug all that stuff in where the y is right there. So I'm actually going to just cheat a little bit, and I'm going to erase this, and I'm just going to rewrite the original function, x to the 3/4 square root of x squared plus 1 over 3x plus 2, plus 2 to the 5th. That is your derivative. And if you had done it using the product and chain and quotient and all that kind of stuff from the original, probably would not look like this. It might be the right answer, but it wouldn't look like this. So you might ask yourself, Well, if I could do it the other way, why would I go ahead and do it this way? Well, maybe you would, maybe you wouldn't. But there are functions where you pretty much have to do it this way. You have a function that maybe looks like this one. Y equals x to the square root of x. Okay, that is not a power function because the exponent itself is a variable. It's also not an exponential because the base is a variable. This is what is actually called an iterated. I keep remembering. Iterated? I think there's two R's in that word. Iterated. That's because you have a variable raised to a variable. That's what's called an iterated function. Okay, not something that we usually deal with in some of our algebraic classes up till now. So how do we take the derivative of an iterated function? Well, really using natural logs is the easiest way to do it. So I'm going to take the natural log of both sides. And the reason we do that is because now on the right side, I can use properties of logs to bring that square root of x out to the front. And now what I've created is a product rule, which I can actually take the derivative of. So we're going to take the derivative of the right side of the equation. Product rule. Derivative of the first term was 1/2 x to the negative 1/2 times the second term, natural log of x, plus derivative of the second term, 1/x times the first term, square root of x. Derivative of the left side, 1/y, dy over dx. Solving for dy over dx means multiplying both sides through by y. So let me clean up the right side, and then I'll multiply everything by y. So I've got a square root of x, which has to drop into the denominator on the first part. So it'll be natural log over 2 square root of x plus. In the next piece, it's really a square root of x over x, which is the same as x to the 1/2 power over x to the first. When you subtract those exponents, you get x to the negative 1/2. So really what you get here is 1 over the square root of x. And I'm multiplying both sides by y, so I put that in a big bracket. Y was x to the square root of x. And that's your derivative. Okay, that is not something you could do using our standard rules that we've done up to this point. All right, now we're going to talk about derivatives of inverses in general. So just inverse functions in general, not necessarily inverse trig or something like that. The idea is, remember this, since inverse functions switch their domain and range, it's part of the definition of inverses, oops, not domain and inverse, it's talking and writing what I'm actually saying. Inverse functions switch their domain and range. It follows that when we want to find the derivative of an inverse function at a specific point, we will also switch the domain and range of that point to evaluate the derivative. So the general formula for this, and it's a little bit harder to understand, is that if I'm taking the derivative of an inverse function, f to the negative 1 inverse function, with respect to x, I'm going to evaluate that instead of at the x value, I'm going to evaluate that at the y value. So when you take the derivative of an inverse function of x, you're going to evaluate it at the y value, which is the same thing as taking 1 over the derivative of the function of x, the actual function, not the inverse, evaluated at the x value. Okay, not exactly the easiest thing to see, but basically what you're doing is you're switching the domain and range, and when you're doing the inverses, you're actually going to take the reciprocal of the derivative of the original function to get the derivative of the inverse. The problem is sometimes finding that original function is not so easy to do. Let's at least see one example real quick here of what this could be. Let 1, 2 be a point on the graph of f of x, which is given here. So we're given an original function, we're given a point. We want to find the derivative of the inverse of this at 2. Well, that makes sense. If I want to find the derivative of the inverse, I'm going to evaluate that derivative at its y value. But the problem is finding the inverse of this function is extremely algebraically difficult. So that's where this nice little formula comes in. It says if I want to find the derivative of the inverse at the y value, I can do 1 over the derivative of the regular function at the x value. So let's find, first of all, f prime of x, because that's the derivative of the actual function. So that's 5x to the fourth plus 2. According to our function, according to our formula, if I want to find this derivative, I'm going to do 1 over f prime at the x value. Well, the x value here was 1. So if I plug 1 in here, I'm going to get 5 plus 2, which is 7. So the derivative of the inverse function at 2 is going to be 1 over the derivative at 1, which is 7. So we get 1/7. Okay, again, not the easiest concept there. And the way this is presented a lot of times in problems, you really have to think through these things to be able to figure them out. But in general, that's it. All right, and the last thing I'm going to cover, and if you're like not into the proofs of things, then you can pretty much stop the video right here. But if you want to see why the derivatives of inverse sine and inverse tangent are what they are, then that's what we're going to do right here to finish up the video. So let's start off with finding the derivative of inverse sine of x. We know it's supposed to equal 1 over the square root of 1 minus x squared. So we know that's what's supposed to happen. So now let's actually make it work. Okay, so we're going to start off with the fact that this function itself is the inverse sine of x. If I want to take and find the inverse of both of these, I can take the sine of both sides. So if I take the sine, let's put it in green, put it in green. Take the sine of both sides. So we'll take the sine of y, which is going to equal the sine of the inverse sine of x. So I'm going to take the sine of both sides. When I take the sine of both sides, that's just going to give me sine of y. And the right side, the sine of the inverse sine simplifies to x because they are composites and they are inverses of each other. So it will simplify to x. Then I can go ahead and take the derivative now of both sides of this equation. When I take the derivative of sine of y, it is cosine of y dy over dx. And then the derivative of the right side is 1. Ultimately, I'm solving for dy over dx. So I will take and divide both sides by cosine of y. All right, we're getting closer because at least I've got to the form where it's 1 over. So now what we have to do is we have to set ourselves up a little triangle to figure this out. So this right here would be our angle y. If I want to do what y is, well, y started off as, cosine of y is going to be the adjacent over the hypotenuse. And the adjacent, because we define cosine of y, all right, hold on, scratch what I just said. Let's go back. I apologize. The sine of y is defined to be x. That's right here. Sine of y is defined to be x. And the sine is the opposite over the hypotenuse, which is going to be x over 1. We can find the missing side here because the missing side we can use Pythagorean theorem. Using Pythagorean theorem, what you get is the square root of 1 minus x squared. So then what you should be able to see is that the cosine of y is the adjacent over the hypotenuse, which is square root of 1 minus x squared over 1, or just square root of 1 minus x squared. And that's what we were looking for when we took the derivative. Okay, tangent is actually just a little bit easier to do. It does involve knowing your properties, but it's a little bit easier. So if I want to take the derivative of the inverse tangent of x, again, we'll start off with the idea that y equals inverse tangent of x. If we take the derivative of both sides, I'm sorry, not take the derivative, wow. We take the tangent of both sides, what we end up with is the tangent of y. The tangent of inverse tangent just gives you x. I can then take the derivative. So the left side will be secant squared y dy over dx equals 1. Dividing both sides by secant squared gives us 1 over secant squared y. But if you remember, secant squared is the same thing using a Pythagorean identity as tangent squared plus 1. And tangent x is, tangent y is defined to be x. This right here should have been a y. I don't know why I wrote x. I'm getting ahead of myself. So we get 1 over x squared plus 1 because tangent squared of y was defined to be x. So that is why the derivatives are what they are. Again, not something you probably want to waste your time developing. Best just to memorize them. But there you have your proofs.